Good morning, students. As we are discussing the chapter probability and we have discussed few types of events, today we are going to discuss one important type of event, that is mutually exclusive events. Now, in order to understand what are mutually exclusive events, let us take one simple example. If I take one random experiment of rolling a die, okay, and we know the sample space will have these six numbers 1 2 3 4 5 and 6, right? And now if I define, let A be the event of getting even number and B be the event of getting odd number, right? Now, according to this definition of A event, the A event will have the outcomes 2, 4 and 6, and B event will have the outcomes 1, 3 and 5. Now, when I take the intersection of these two subsets, right, A subset and B subset, when I take the intersection of these two subsets and it is coming 5. Now if you remember, in the set theory we have learned the types under types of sets. The two sets will be called disjoint sets if they have nothing in common. That means if the intersection of two sets is coming 5, then the sets are called disjoint sets. And here, because we are defining two events A and B, and these two events are actually the subsets of the sample space. Now if the intersection of these two subsets comes 5, then I will say these two events A and B are mutually exclusive events. Okay, these are called mutually exclusive events. So in other words, how we can define? We can define in general two events A and B associated with the sample space of a random experiment will be called mutually exclusive events if they cannot occur together or simultaneously at the same time, right? So when we roll the dice, it is not possible to get the even number and odd number at the same time. That is not possible. So getting odd number, getting even number, when I roll the dice, these two events are mutually exclusive events, right? The other example also we can have, if I say I am tossing the two coins, and we know the sample space will have HH, HT, TH and TT. If I say let E be the event of getting two heads and F be the event of getting two tails. Now again, these two events, that means when I look at these two subsets, the intersection is 5. So E intersection F is coming 5. What does it mean? These two events E and F are mutually exclusive events, right? So this is how based upon or depending upon any sample space given associated with some particular random experiment, we can easily define the events which will be mutually exclusive, as well as we can describe those events also. Okay, so this is the definition and the explanation of mutually exclusive events. And now the next is exhaustive events. Now what are exhaustive events? Let us discuss. Now, exhaustive events are those events, if I just take the same sample space as we have discussed earlier, and the event we define, the A event was getting an odd number, and if I say B event getting an even number, right, and these two events are associated with the same sample space 1 2 3 4 5 6, that means rolling a dice. And if I take the union of these two subsets A and B, I am getting the sample space, right? So the events that I am defining on a particular experiment, random experiment associated with some sample space, then the events will be called exhaustive events if the union of those two events or three events or four events giving me the complete sample space. Okay, so in general, how we can define it in general, the events like E1, E2, E3 up to so on, if I have n events associated with sample space S of some random experiment such that E1 union E2 union E3 up to so on union En, when I take, it is giving me sample space. Then these events, all Ei's events where I is less than or equal to n and n is a natural number, are called exhaustive events. Okay, these will be called then exhaustive events. So when I define two or three or four events on the same sample space and the union of all those events is giving me back the sample space, that means those events are called exhaustive events. Okay, so if I take the example, tossing two coins, so we have this sample space, right? And if I define, let E be the event of getting at least one head, F be the event of getting two tails, right? Then E union F is giving me complete sample space. So E and F are here. Which events? These are exhaustive events. Now, one more thing I am going to explain here. If I am taking the same example as I have taken here, tossing of two coins together, E event I have defined of getting at least one head. So according to this, E event will have HH, HT and TH, right? And F event is having only one outcome, that is TT. Now what is happening here, when I am taking the union of these two events, I am getting the sample space. But if I am taking the intersection of these two events, it is coming phi, right? So such events for which if the union of all those events is giving me sample space and they are pairwise mutually exclusive also, remember they are pairwise mutually exclusive also, then these events will be called, then these events E and F are here called mutually exclusive and exhaustive events, right? Mutually exclusive and exhaustive events, right? So in general, if we say all those events, right, like E1, E2, E3 up to so on En associated with the same sample space, right, they will be called mutually exclusive and exhaustive if the union of all those events is giving me sample space. And if I take pairwise intersection, it is coming phi, then the events will be called mutually exclusive and exhaustive events, right? So in general, if I say, this is how it will be written. So if I define like E1, E2 up to so on, En events are there, like such that if I take the union of all those events, I is varying from, it is 1 to n, it is giving me sample space, and EI intersection EJ is phi, where I is not equal to j, and both I and j, they are less than or equal to n, and n belongs to natural numbers, right? Pairwise intersection is phi, union of all those events is S, then these events are called mutually exclusive and exhaustive events, right? So this is the last part of the exercise 16.2. Now the remaining sums of the exercise are based upon these two types only, where we will be defining the events which are mutually exclusive or they are mutually exhaustive or both are there, and then we will be describing. So let us do few sums based upon this type. We have here sum number 4. 3 coins are tossed once. Let A denote the event 3 heads show. B denote the event 2 heads and 1 tail show. C denote the event 3 tails. And then show that and D is the event. C is the event 3 tails. Denote the event this. Show that D is the event a head shows on the first coin. Okay. Which events are mutually exclusive? Which are simple or which are compound? Right? So let us do this sum number 4 of exercise 16.2. Right? Sum number 4. The experiment is here. 3 coins are tossed. So when 3 coins are tossed, we will have how many outcomes? There will be 8 outcomes or sample points, we can say. Now A is the event 3 heads show. Okay, 3 heads. That means A will have H, H, H. There will be only one outcome. B event is given as 2 heads and 1 tail show. So we want 2 head and 1 tail. So according to this definition, the B event can be defined as HHT, HTH, THH. So 2 heads and 1 tail are there. C event is given as 3 tails. Okay. So all 3 tails only. So it will be T, T and T. There is only one outcome. And D event is given a head shows on the first coin. So head on first coin. So when head is on the first coin, first of all H, H, H will be there. Then H, H, T will be there. H, T, H will be there. Okay. And what else? H, T, T will be there. Right? So H, 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 T, H, T, H, H, T, T. That's it. I think these 4 outcomes will come when head is on the first coin. Now we have to check which events are mutually exclusive. So first of all, we have to find the simple events also. So if you remember the definition of simple event, the event with one outcome only is called simple event. So yes, A is simple event, right? Similarly, C is also simple event. B is compound event. And D is also compound event. Right? Now, which are mutually exclusive events? Mutually exclusive events are those events for which intersection is phi. So, if I take A intersection B, okay, so A intersection B, what is coming? Triple H, and there is no triple H, so A intersection B is phi, right? Then A intersection C is also phi, but A intersection D is not phi. Okay, B intersection C is also phi, but B intersection D is not phi. Then C intersection D is also phi. So what we will say, which implies A and B, comma, A and C, comma, B and C, comma, C and D are mutually exclusive events, right? So these are mutually exclusive events. So now in sum number 4, this is sum number 4, that's it. Sorry, in sum number 5, we have to describe. Describe means we have to define which 2 events will be mutually exclusive and which will be mutually exhaustive or mutually exclusive and exhaustive and so on. So let us discuss few parts of sum number 5. So let us do sum number 5. Again the experiment is same. 3 coins are tossed. We have to describe first of all 2 events which are mutually exclusive. Now mutually exclusive means the events for which intersection is coming phi. Same experiment, 3 coins are tossed. Here we have many examples. 4 examples we have already here, for which the events are mutually exclusive. So getting 3 heads and getting 3 tails, these two events can be defined as mutually exclusive. Getting 3 heads and then the next event getting 2 heads and 1 tail, these two events are also mutually exclusive. B and C are also mutually exclusive. So anyways, let us do it properly. So let us discuss here sum number 5. Sum number 5, the experiment is 3 coins are tossed. 3 coins are tossed. Let us write down the sample space, then it will be easy, to define the events. So triple H, then HHT, HTH, THH, 2 heads are over. Now let us write for 2 tails, TTH, THT, HTT, okay, over, and then last triple T. 3 heads, 2 heads, 1 head, and no head. 2, 4, 6, 8. All the 8 outcomes are there. Now we have to write down first is 2 events which are mutually exclusive. Okay, 2 events mutually exclusive. So I think if I write down, let A be the event, A be the event of getting 3 heads and B be the event of getting 3 tails, right? So A is H H H, B is T T T, and A intersection B is phi. We have to show all these things. Okay, first we will define, then we have to show also. Okay, yes, if I am taking these two events, the intersection is coming phi, it means they are mutually exclusive events. Okay, the second part, 3 events which are mutually exclusive and exhaustive. Okay, now we have to define 3 events and they have to be mutually exclusive also, and they must be mutually exhaustive also. Mutually exclusive means pairwise the intersection should be phi. Mutually exhaustive means if I take the union of all these 3 events, I must get the sample space, right? So let us see now. They should be mutually exclusive and they should be exhaustive also. So we can define, let A be the event. So here actually comes the important part. We have to think how I can define the events, like the intersection of A intersection B should be phi, A intersection C should be phi, B intersection C should be phi, and when I take the union, okay, the union must give me all the complete sample space, right? So if I say let first event be getting 3 heads, okay, and then second event getting 3 tails, and let the third event be like at the most 2 heads. But if I say at the most 2 heads, then the problem will be there. At the most 2 heads, that means no head will also come, so triple T will come there also. So if I say, okay, if I define getting at least 2 heads, getting at least 2 heads, that means 2 and more, so these 4 outcomes will come in the event. And the second event, if I define, let B be the event of getting 3 tails and C be the event of getting 1 head, getting at least 2 heads, getting 1 head only, and getting no head. And then definitely this intersection, no intersection will be non-empty, means all intersections will be empty also. And when I take the union, I am getting the complete sample space. Now you people must be thinking like how we will think. So these things will come in practice only. From the sample space I can divide the sample space into three parts or four parts in such a way that when I take the union I am getting the complete sample space, but when I am taking the intersection, intersection should come 5, right? So if I define, let A be the event of getting at least two heads, right? So A event will have HHT, HTH, THH, two heads, and now more than two, that will be triple H. Now B be the event of getting exactly one head. Now when I say exactly one head, so B will have HTT, THT and TTH, right? And C be the event of getting no head. No head, or you can say getting three tails, right? So C will be equals to T, T, T only, right? All three T's only. So when I take A intersection B, we are not getting any common element. B intersection C, no common element. A intersection C, no common element. But if I take A union B union C, I am getting the complete sample space, right? So this is how we can define the events, right? Now I'm leaving some number 5, third, fourth, fifth part for you people only. You have to think and then do the sums. Sum number 6 already I gave for the homework. Sum number 7 is again based upon sum number 6 only, and we have to state true or false and giving reasons for your answer. First is A and B are mutually exclusive. Now what is A event? A event is defined getting an even number on the first die, and B event is getting an odd number on the first die. Definitely on the first die at the same time odd and even numbers cannot come simultaneously. So yes, it is true, A and B are mutually exclusive. Now the next is A and B are mutually exclusive and exhaustive. So now we have to think whether A and B are mutually exclusive. Exclusive for sure. Are they exhaustive also or not? So exhaustive means when I am taking the union of these two sets A and B, am I getting the complete sample space or not? Okay, so if I am getting the complete sample space, then they are mutually exclusive as well as exhaustive. So if I just observe it, or if you want, you can write down all the sample points for these two events, and there you can show yes, the union is equal to sample space. Okay, and then the answer will be true. Yes, they are mutually exclusive and exhaustive, right? The next is, so I hope you people remember dash is representing the complement. Complement means not A event. Okay, so you people can complete the sums of the exercise now. Third part again, A is equals to B complement. What is B? B is getting an odd number on the first die. So what will be the complement? Complement means not getting an odd on the first die. So if odd number is not coming on the first die, what will come? Even number will come. So yes, again it is true only, right? So like that you people can check the remaining parts of this exercise, and you will be able to complete it. The next thing that I want to explain is how we are taking the probability of event A or B. Okay, we have discussed the events A or event B. So if you remember, we have discussed the event A or event B. Okay, event A or event B, it will be having all the sample points such that this either belong to A or this omega either belong to B, right? This is the event A or event B. Now we are going to discuss the probability of an event. Okay, how we will calculate the probability. Now calculating the probability is same only. If I have the sample space, like again I am tossing two coins, right? I am getting these four sample points in the sample space, and if I define, let A be the event of getting at least one head, right? At least one head means I will have these three outcomes only, and I have to calculate the probability of this event A, right? Then the probability of this event A will be equals to, number of outcomes favorable to event A divided by, again, total possible outcomes, right? So if event A is having, there are three outcomes in the event A, so the probability will be, what is that? It will be 3 divided by total. So let me write down here. So we can write down number of outcomes favorable to event A divided by total number of outcomes, right? In other words, also, how we can write down, if number of elements in number of outcomes in the sample space, let it be let us say it is capital N, okay? Or instead of capital N, let it be small n only, but n is representing here, okay, fine, let it be capital N, and number of outcomes in the event A is, let it be M, right? Then the probability of A event will be M divided by N, where M is the number of outcomes in A event, N will be the number of outcomes in the total sample space, right? Now this is true when we know that all the events are equally likely events. I hope you people know what does it mean, equally likely events. That means the chances of occurrence of each and every outcome in the sample space is same. So when I toss the coin and it is unconditional unbiased coin, okay, then the chances of coming of head is same as the chances of coming of tail. So that is why the complete sample space, if it is having two sample points, the total probability of the sample space is 1, okay, and that one we divide equally among the sample points. So here if I have 4 sample points, right, the number of elements in the sample space is 4, and we know the probability of sample space is always equal to 1, right? Then the probability of each and every outcome will be 1 divided by 4. Okay, we will just divide the total probability among these 4 outcomes in equal rate, in equal proportion, right? So this is the probabilities of equally likely outcomes. And now the next that I want to tell you, if I have to calculate the probability of the event A or B, okay, this is given by probability of event A plus probability of event B minus probability of event A intersection B. This is the formula to calculate the probability of the event A or B. And if you just observe one thing, the formula is very similar to calculating the number of elements in the set A or B, right? N of A plus N of B minus N of A intersection B. The same formula, instead of N, what do we have? P, that is the probability, okay? So this formula we will use in order to calculate the probability of event A or B. And if the events are, mutually exclusive events, right? So if A and B are mutually exclusive events, that is A intersection B will be phi. If A intersection B is phi, that means the probability of A intersection B will be 0. So the probability of A union B will be equals to probability of A plus probability of B. So this is the another result under this condition only, right? Otherwise, in order to calculate the probability of event A or B, we will use formula probability of A plus probability of B minus probability of A intersection B, right? So that's it for today. The remaining topics we will discuss in the next class, and I hope you people will be able to complete your exercise 16.2. Thank you, students.